I want to invest some time in the investigation of the properties of the RLSM procedure. The RLSM procedure, recursive least square method estimation procedure, will be important for the implementation of both the explicit and the implicit self-tuning procedures in adaptive control. So the program implementing RLSM is written, in my case, in the CC language, which is control command, but of course it is not much different from a procedure written in the MATLAB code. But we will start from creating a data array that contains input and output measurements for a system with 5 inputs and 1 output. So first of all, I have to specify the total number of observations, which is 150. The next, what I will do, I will specify the mean values of 5 input variables. Specifically, these mean values are 1, 2, minus 3.6, 8, and 5. Then I have to represent these mean values by a diagonal matrix. The next, what I will do, I will create inputs. The total of 150 inputs, and these inputs will be defined as random signal plus their mean values. So basically I'm getting 150 times 5 matrix, and this matrix is filled with the observations of input variables. And then I define the output. Output is the matrix array X that contains input observations times the column containing coefficients. And these coefficients I presume to be unknown coefficients. I also want, and you can see it here, to inject random signal that represents the output noise in the system. So this random signal is injected only in the Y measurements, in the output measurements. The next, what you can see, is the implementation of the RLSM procedure with forgetting factor, and this forgetting factor is equal, in my case, initially, to 1. Having forgetting factor equal to 1 implies that our procedure is just a traditional RLSM procedure that has infinite memory. This is the definition of the initial matrix P. If you remember, we recommend matrix P to be defined as unit matrix times some constant, positive constant, and this positive constant here is equal to 0.01. This is the column of initial values of 5 parameters of the model. We presume that model parameters initially are unknown, and the next what we do is exactly the implementation of the RLSM procedure. First of all, we compute matrix K, the Kalman gain, and this formula is very consistent with the definition of the Kalman gain in the RLSM procedure. The next, you can see the updating of parameters of the mathematical model. This is the new value of the parameters. This is the old value of the parameters. This is the Kalman gain. This is the error, the discrepancy between the measured output and the output calculated using the old coefficients. Now, what I'm doing here is I am picking up coefficient number 1 because later I will plot it. I will plot coefficient number 1 versus the iteration index. The next, you understand, I have to compute matrix P that I will use for the next step of the RLSM procedure. This is the end of the loop. Here I have coefficients A, and here I have coefficients A calculated using the LSM procedure. And the last what you can see is plotting of the coefficient number 1 with respect or versus the iteration number. And here are some results of our numerical experiment. So first of all, I have the set of coefficients that are true coefficients. These are the coefficients that were originally utilized to compute the output y. Here you can see coefficients calculated using the least square method procedure, not RLSM, but the least square method procedure. And LSM gives us values that are quite close to the values of the true coefficients, or true coefficient values. Here what you have are the values of the same coefficients calculated by the RLSM procedure utilizing the total of 150 steps, 150 iterations of the RLSM algorithm. If you would compare these values, they are very, very close, and they are also close to the true values of unknown coefficients. So you may conclude that although the output measurements are contaminated with noise, this noise does not adversely affect the estimation process. Our RLSM works. And just for comparison, I am giving you values calculated by the same RLSM procedure, but utilizing the total of 1,000 iterations. And what you can conclude is that after 150 iterations, we're not getting much of additional accuracy by running RLSM procedure for longer and longer time. So it looks like 150 iterations is sufficient, and everything what we can do beyond 150 iterations is unnecessary. So the next what I would like to do, I want to show you the convergence of the estimate of the coefficient number 1. If you remember, in the computer code, I made some provision for creating an array of coefficient number 1 for each of the iterations, and here this coefficient number 1 is plotted. However, the first plot is done for the parameter, for the initial value of matrix P defined as 10 times unit matrix. I want to remind you, let me go back. This is the definition of the initial matrix P that is used in the RLSM procedure. And here I have matrix P initial defined as 0.01 times unit matrix. Here you see a result that was obtained when matrix P initial was defined as 10 times unit matrix. Here matrix P initial is defined as 1 times unit matrix. Here matrix P initial is defined as 0.1 times unit matrix, and finally here matrix P initial is defined as 0.01 times unit matrix. And I made a statement that this positive constant, here it is 10, here it is 1, here it is 0.1 and 0.01, this positive constant works as a constant gain in a simple control system, as a constant gain in the feedback. If this constant gain in the feedback is large, we're getting very fast convergence, a very short settling time if you prefer control terminology, and the high overshoot. If we would reduce this coefficient in the feedback, or if we would reduce this positive constant in the definition of matrix P initial, we're getting less overshoot and we're getting slower convergence of the procedure. Or if you prefer verbiage of the control business, you're getting larger settling time for the transient process, for the system step response. If I would decrease coefficient in front of unity matrix in the definition of matrix P0, if I would decrease it to 0.1, you can see very slow convergence, and as a matter of fact, within 150 iterations, we never reach the full convergence of the procedure. And finally, if I would make this constant equal to 0.01, then the convergence process is so slow, or the settling time is so high, that we never reach the steady state, if you're talking step response, or we never reach the true value of the coefficient number 1. The true value is 5, as a matter of fact. So you see a very good illustration of the effect of the positive constant in front of the definition, or in the definition of the initial matrix P in the RLSM procedure. You have to choose it experimentally, I guess. And if I would be running this procedure, obviously I would choose this constant equal to 10. You have initial overshoot, but then you're reaching the true value that is equal to 5 for this particular coefficient. And let me show you. Let me go back. The true coefficient is exactly 5. Coefficient number 1. The next, what we will do, we will consider the role, or investigate the role, of the forgetting factor. You know, because of the forgetting factor, we have the ability to establish the memory of the procedure. And memory of the procedure at any moment of time is effectively the number of measurements that primarily contribute to the estimates of the unknown coefficient. And I'm working with the coefficient number 1. So what happens in this case? I'm showing you the effect of the forgetting factor. First of all, here the forgetting factor is equal to 0.5. The memory of the procedure is 1 divided by 1 minus 0.5, which looks like at any moment of time. The estimate is based on 2 previous measurements of input-output data. Since we have the noise, you can see the effect of this noise, and since we're using only 2 measurements each time when we want to compute the value of the coefficient, you can see the manifestation of this noise. We're getting the convergence process affected by noise. Nevertheless, we're getting more or less reasonable convergence of the RLSM estimation. The next, what you can see, is a situation when effect of noise is quite reduced. The memory of the procedure is 1 divided by 1 minus 0.8, which is 5, which means that each of these estimates is based primarily on the 5 input-output measurements. So we're getting the effect of averaging out noise, because now the averaging is performed on 5 observations. And later, you can see even more smooth convergence curve. As a matter of fact, it is quite perfect convergence curve. In this case, forgetting factor is 0.98, which means that the memory of the procedure is 1 divided by 1 minus 0.98, which is what? 1 divided by 0.02, which is what? 20. So we perform averaging on 20 observations of input-output variables, of input-output measurements, and we're getting reasonably good rejection of the measurement noise, and you can see that the entire process is quite smooth. Convergence process is not affected by noise. The next what we want to see is to investigate the ability of our procedure, RLSM procedure, to track time-dependent coefficients. So in these numerical experiments, you have to realize that we compute coefficients, real coefficients, we estimate real coefficients, but these real coefficients are changing with time. And our observations also are affected by the noise or in the measurement channels. So first of all, let's figure out how to evaluate the goodness, the success of our procedure, RLSM procedure. RLSM procedure supposed to compute parameters of a model. This model is accurate if we manage to track time-dependent parameters of the process, and this model is not that accurate if you fail to track time-dependent parameters of the process. Now, how to assess the goodness of the model? To assess the goodness of the model, we use the coefficient of determination. I don't want to talk much about the coefficient of determination, but let me tell you this. This coefficient of determination is defined as the full variance or true variance of the measured output minus variance of the error or discrepancy between the output of the real process and the output of the model, divided by the variance of the output, or variance of the output variable y. You know, if our model is good, the coefficient of determination is close to 1. If our model is not so good, coefficient of determination is approaching 0. It's always positive. And it could be anything between 1 and 0. It is equal to 1 if model is good, and it's equal to 0 if model is very bad. So what you can see here is that we choose the coefficient, the forgetting factor equal to 0.8, and we plot the coefficient of determination. It is green as we run the RLSM procedure. So initially, this coefficient of determination is low, and it is low because the goodness of our model is not so good. The goodness of our model is adversely affected by the measurement noise. But as we keep running the procedure, the measurement noise is being rejected, and eventually the value of the coefficient of determination approaches 1. However, you can see significant variability in the coefficient of determination due to measurement noise. And as a matter of fact, measurement noise affects the value of coefficient of determination, even as it approaches to value of 1. And then we chose forgetting factor equal to 0.01. Now our estimation of coefficients is based on 1 divided by 1 minus 0.9. So we basically estimate coefficients based on 10 most recent measurements, and we're getting coefficient of determination that still oscillates, but it does not oscillate that much, and eventually it very nicely approaches to the value of 1, which means that we're getting, on one hand, the ability to reject noise, on the other hand, we're getting the ability to track time-dependent parameters of the real process. If I would use coefficient of determination equal to 0.95, then the memory of the procedure becomes much greater. We have the ability to reject measurement noise, but we're failing with the value of coefficient of determination because we're losing the ability to track time-dependent parameters of the process, and this is seen very explicitly in this drawing. Here the coefficient of determination is equal to 0.999. The memory of the procedure is 1,000 data points, and with such a memory we fail to track time-dependent parameters of the process, and therefore in the beginning coefficient of determination is high, but then it drops due to the fact that parameters of the real process change, but we fail to track these parameters. You know, for value of the forgetting factor of 0.99, we have a kind of situation when in the beginning coefficient of determination is reasonably high because we are quite successful with rejection of noise, but with time parameters of the real process drift away from the initial values, and they keep drifting away, and the coefficient of determination increases due to our inability to follow, to track time-dependent parameters of the real process. Well, I guess this is the discussion, the verbiage that presents the further discussion of the realities that I just talk about. The next, what I want to do is to implement the RLSM in the explicit or indirect self-tuning procedure of adaptive control. What are we doing in this explicit or indirect self-tuning procedure? In this explicit or indirect self-tuning procedure, what we actually do, we explicitly estimate unknown parameters of the control plant, and as soon as these parameters become known to us, we use these values of these parameters in order to redesign the feedback controller and the filter to modules of the control system. I want you to take a look at the block diagram that explains the principle of operation of this explicit self-tuning procedure or indirect self-tuning procedure. First of all, I want you to see the process or controlled plant with the control effort that drives the plant and the output of the plant. Obviously, this process is also affected by disturbance, but disturbance we do not measure. We actually reject this disturbance using the negative feedback controller. So we're not talking much about the disturbance when we look at this diagram. The next, what you can see, that we monitor the control effort or the input signal of the process, and we monitor the output of the process, and the block, we call this block the data acquisition block. This block performs the discretization of the input-output variables, but this block does a little bit more because this block is used for tuning, for estimating parameters of a very particular model or very particular transfer function of the process. The next, what you can see, is the RLSM procedure that picks up data created by this data acquisition module, and it converts this data into numerical values of the parameters of the model or parameters of the transfer function. And these parameters are utilized by the block that we call controller design, and this block controller design provides information for the feedback controller of the system and provides information for the filter in the reference channel. I want you to realize I call it feedback controller. It's not feedback controller. It's actually the filter in the reference channel. I will change the, this is a mistake, and I will change the name of this block. So let me go back and let me be more specific in discussing individual modules of this block diagram. First of all, it is the process. For the process, you have to realize that we have some input, which happens to be the control effort. This input is defined by the control circuitry. I call it U. And this input is applied to the controlled process, and this input is converted into the output according to the true, unknown to us, but true function representing the properties of the controlled plant. And obviously the output is calculated based on the input, based on the disturbance, and according to the function phi that we assume to be unknown to us. This function could be nonlinear, this function could be dynamic, and so on and so forth. But this is as much as the control, controlled plant module does for us. The next is data acquisition block. So, for the data acquisition, we have the input signal, that is signal U, the control effort. It's a continuous time signal, but we discretize the signal, and after discretization, we're getting a sequence of numerical values of this input. The same is done with the output. However, I want you to realize that we accumulate this data, we perform data acquisition, not just for the sake of data acquisition. We perform data acquisition in order to provide information for the updating coefficients of our mathematical model. This process we represent by a mathematical model that is linear model, and it is a dynamic model. It is given by a difference equation. This difference equation, for the purpose of learning, I would come up with a very particular configuration of this difference equation. This difference equation defines output y at time k plus 3 equal to output y at time k plus 2 times some coefficient. And then what's involved is output k plus 1 times some coefficient. And then I have output yk times some coefficient. And then I have the input, the control effort at time k plus 2, k plus 1, and k, multiplied by the appropriate coefficients. And here I have the expression that we should call the forward difference model. And here I have exactly the same model, but I turned it into a backward difference model. System is the same, but everything depends whether I use k plus 3 as the output variable or y of k as the output variable, and then the input variables are variables picked from the past. Here, the output variable is a variable picked from the future, and I have the input variables picked from the future and present. So I would say that there is no difference between this definition of the difference equation and this definition of the difference equation. However, the forward difference could be converted into this very conventional transfer function in the z-domain transfer function. Z-domain transfer function. Now, it looks like we have limited ability to pick up values from the future, and therefore we will be better off picking values from the past. So instead of working with value k plus 1, k plus 2, k plus 3, I would use values k minus 1, k minus 2, k minus 3, uk minus 1, k minus 2, k minus 3. So one way or another, for our specific model, represented by a transfer function of this type, third order transfer function, third order z-domain transfer function, it looks like if you want to apply RLSM procedure, this is how we should define the vector of the input variables, and this is the output variable that corresponds to this vector of input variables. The rest is quite understandable. Now we are prepared to use this measurement of the output and this measurement of the input vector in order to perform particular iterations of the RLSM procedure. So at this point, the data acquisition task for the step, for the iteration number k is done, and we can go into the implementation of the step number k of the RLSM procedure. The RLSM procedure will operate on a step-by-step or iteration-by-iteration basis. But before we will start the implementation, the running of the RLSM procedure, we have to provide some initial values for the procedure. Some initial conditions for the procedure have to be provided. What do we have to provide? You still remember that we have to provide the initial definition of matrix P0. This matrix P, in our case, is a 6 by 6 matrix. And then you realize that we have to provide the initial definition of unknown parameters, the first set of estimates. And if I know nothing about the controlled plant, I will make all these coefficients equal to zeros. However, don't forget, we use RLSM procedure in high-tech environment. And in the high-tech environment, many smart physicists, Many smart engineers normally invest time to get some preliminary values of the parameters of the transfer function of the control plant. In real life, we never start from complete zero knowledge of the control plant. We have the so-called best guess for the control plant, and this best guess could be utilized for the definition of initial values of the parameters of the procedure, parameters of the control plant. One way or another, we're supposed to have matrix P0, initial matrix, and initial set of parameters of the mathematical model, or parameters of the transfer function that we will be estimating using the RLSM procedure. Now I want you to realize that since this is the configuration of our data, we should start our procedure, RLSM procedure, not from k equal to 1, but from k equal to 0, which means that we have to accumulate, in our case, 4 measurements of the input and output data. If k is equal to 4, then we will have no problem for providing this initial value of the output and the initial value of the input vector. What do we do now is we compute Kalman gain, and this Kalman gain at our first iteration will have index 4 because it will be based on matrix P with index 3. It will be based on values of these parameters for k equal to 4. This is a unit matrix. This is vector of input variables for k equal to 4. This is matrix P, the initial value of matrix P, and this is the vector of input variables. And then it's good to mention to you that P3 should be equal to the initial matrix P, and initial matrix P we define as some kind of positive constant, probably chosen by experiment, times unit matrix. When the Kalman gain has been calculated for k equal to 4, then for k equal to 4, for the iteration number 4, we will update parameters of the mathematical model. And what you can see here is the set of parameters resultant for iteration number 4 is equal to the set of parameters from the previous iteration, Kalman gain, the measurements of the output, the measurements of the input vector, old coefficients, and this is the computation of the new set of coefficients. Now, since we started our RLSM execution from k equal to 4, then the A3, the initial set of parameters, is equal to A0, and A0 probably would reflect our best guess model or best guess information about the control plant. The next is step number 3, and you can see that we compute matrix P4 that will be used at the step of the Kalman procedure, a number k plus 1, or for k equal to 5. It's not used for the iteration number 4. It will be used for the next iteration. And then what we have to do, we just obtained for k equal to 4 parameters of the mathematical model, and these parameters must be interpreted as parameters of the transfer function. This is done by showing vector AK, where vector AK is the set of parameters resultant from the iteration number k, and this vector includes A1k, A2k, up to A6k, and we have to express these parameters as the parameters of the numerator and parameters of the denominator, or parameters of the denominator first, and then parameters of the numerator of the z-domain transfer function. So, as a matter of fact, the iteration number k has resulted in the numerical definition of the z-domain transfer function of the control plane. But this definition is as good as the parameters established at the iteration number k in our case. Nevertheless, as soon as you will get this expression for the transfer function, we should perform controller design. When we perform controller design, and let me go back to our diagram, for the controller design, we're supposed to have the desired z-domain transfer function of the closed loop system. It will not change during the entire self-tuning procedure. It is constant. Where this transfer function comes from. This transfer function comes from the design specifications. Each time when we design a controller, we have to start from some kind of design specifications. So, in our case, the design specs come from the customer probably, and the best what we can do is to come up with an S-domain transfer function that reflects the design specifications. This is the S-domain transfer function of the closed loop system, reflecting, as I said, design specs. You know, we can call this transfer function of the model, or model transfer function, because it gives you a very good representation of the desired closed-loop performance of the system we want to build. However, our system will be designed and will operate in the z-domain, and therefore, this model transfer function we will convert into the z-domain model transfer function, and the z-domain model transfer function should be obtained using the computer tool. We will use the zero order hold option for this conversion, and this conversion would be dependent on the chosen time step, delta t. So, by performing this conversion, and you have to perform this conversion only once, we will get the z-domain transfer function of the closed loop system, or model transfer function for our system. And we will use parameters beta 2, beta 1, and beta 0 for the numerator, and parameters alpha 2, alpha 1, and alpha 0 for the denominator of this transfer function. When this is done, the situation is as follows. We just completed the iteration of the RLSM procedure, number k. This iteration has resulted in the parameters beta 2, B2, excuse me, B1, and B0, and this enables us to define the filter in the reference channel immediately. Beta 2, beta 1, and beta 0, they came from the model expression. But parameters B2, B1, and B0 in actuality are the last three estimates of the vector of parameters obtained at the iteration number k. So here are these parameters that are channeled from the RLSM module. And then we have to recall that the feedback controller is supposed to be expressed in this way. The parameters of the denominator are exactly the same as parameters of the denominator in the filter, and they are actually last three components of the vector of estimated parameters that comes from the RLSM module, and the parameters h2, h1, and h0 could be easily calculated based on parameters alpha 2, alpha 1, and alpha 0 of the model transfer function, and parameters a2, a1, and a0 that come from the or as first three components of the vector of adjustable parameters that comes from the RLSM block. So at this point, our controller design has been completed, and we can complete this controller design task each time when RLSM procedure would compute new set of parameters of the transfer function. The next what we have to do is to implement the control law. How to implement the control law? Now, we have two modules, two computational blocks representing the control law, the filter and the feedback controller. So first I took the filter. The filter is defined as, the transfer function of the filter is defined as z transform of some output variable of the filter w divided by the z transform of the reference. They are defined by this transfer function. I have absolutely no problem dividing numerator and denominator of this transfer function by z squared, and I'm getting this result. And based on this result, I can obtain an easy backward finite difference that would give me the variable w for time k on the basis of variable w previously defined for k minus 1, w defined for k minus 2, value of reference for k, value of reference for time k minus 1, and value of reference for time k minus 2, and b1 and b0 and beta 2 and beta 1 and beta 0 are parameters of the transfer function. So this finite difference would be responsible for the computation of variable w. I'm doing exactly the same thing with the feedback controller. This is the transfer function, z-domain transfer function of the feedback controller. It's equal to the auxiliary variable v divided by the output variable of the control plant y. Here I have the transfer function. Here I have the same transfer function, but numerator and denominator divided by z squared. And finally, I convert this expression into a backward difference expression. And this backward difference expression defines value of variable v for time k as a function of value of variable v at time k minus 1, k minus 2, a value of variable y at time k minus 1, and time k minus 2. And finally, I define the control effort as the difference between variable w and variable v. And what I have here is very consistent with this diagram. This is the variable w from the output of the filter. Here comes variable v from the output of the feedback controller, and the difference between w and v is the control effort u that is applied to the input of the control plant. And of course, this expression and this expression, they facilitate implementation of the control law in the control computer. What happens next? What happens is very straightforward. We have to increment k by 1, and we have to go back. We have to perform data acquisition. We have to perform RLSM step. We have to perform a redesign of the controller. We have to implement the control law with updated parameters, and then this will be happening in a cycle because k will be equal to k plus 1, k plus 2, k plus 3, and so on. And now I will talk about possible modifications of this procedure. So first of all, the controller redesign does not have to be performed for every k value. You may perform controller redesign for every by skipping m steps of the RLSM iterations. Okay, so the updating of the controller could be performed, for example, for k equal to 10, and then for k equal to 20, and then for k equal to 30. Meanwhile, the RLSM procedure will be engaged for each particular value of k. So, we have to look into the realities of life. We have to figure out how fast parameters of the controller really change. And of course, the next what we have to do, we have to consider the introduction of the forgetting factor. We have to consider the use of finite memory of the RLSM procedure, and then this would help us to address the great compromise, great trade-off between the averaging out noise, measurement noise, and having the ability to track time varying parameters. So this modification probably will be a very practical thing to do. So you will have an opportunity to implement the explicit, self-tuning procedure in your take-home assignment, take-home project, and you will get some additional experience with the use of self-tuning. I want to emphasize that we call this approach explicit self-tuning because this approach implies that we estimate unknown parameters of the control plant in the most explicit form. Look, we're getting coefficients of the transfer function of the control plant. We're getting these coefficients, and we're estimating these coefficients even if they drift, even if they change with time. So we're getting the ability to track coefficients of the controlled plant in the most explicit form. What is good about it? What is good about it is this. This coefficient may represent friction in the bearings. This coefficient could be affected by the stiffness of some springs, for example, stiffness of the oil spring in the flight actuator. And the stiffness of the oil spring will change if there would be water contamination or if would be air contamination. So you see, now some of these parameters will be changing drastically if there is a battlefield damage inflicted on an aircraft. So how a pilot could detect assess the current status of the airplane, for example, by special software that would analyze time-dependent estimates of the unknown parameters and provide some critical information to the pilot. So I would say that in addition to benefits, to control benefits, the explicit self-tuning enables us to have some diagnostic system capabilities that are very important. Now, is it necessary to explicitly estimate parameters of the transfer function and then redesign the controller? Is it possible to redesign the controller without getting involved in the parameter estimation of the transfer function? It is possible. And this part is known as the direct self-tuning. When we subject parameters of the controller to direct manipulation by our self-tuning procedure. In the case of indirect self-tuning, we redesign, first we evaluate parameters of the control plant, and then we redesign the controller. So I have one more lecture for you on self-tuning, and this will be the direct self-tuning.